Hi, I'm Nicholas. I'm excited to be here. About 1.5 years ago, I started my first full-time position at BCGX. That's the data science department of the Boston Consulting Group. There, I work as an AI engineer. I do MLOps, ETL, CI/CD pipelines, basically everything to empower our data scientists. At our company, we build a wide range of AI products. For example, optimization forecast, more of the basic stuff. But in the last couple of months and years, with the growing demands, we build a lot of Gen AI builds, and mostly they start off as POCs. Building such a POC is a great experience. It's a super steep learning curve. It's great to showcase ideas and get quick feedback. But a common misconception we see with clients and with managers is that if you have a ready-made POC, that you can just roll it out to the whole department. And that's unfortunately not the case. From my experience, building a POC is only about 20% of the work. The true work begins when you have to build scalability, when you have to think about how many users will use it, how will your database handle this, and how all the stuff that you kind of forget when you're just building features for your POC. So yeah, I invite you to join me to explore how we can bridge the gap between the concept and impactful scalable solution. To give you a short agenda, I'm going to introduce the application that I personally worked on. I quickly explain the architecture and the data flow, and then jump to the time where we went from POC to product, and what challenges we faced and what changes we had to do to get the application under control and to run it smoothly under significant load. So yeah, for the sake of this talk, let's say our client was a meal kit delivery company, something like HelloFresh, if you know them. They deliver ingredients to your house, ready to cook. This company has a support hotline you can call, and you can ask questions about the recipe. You can complain about missing ingredients and all that stuff. And the company tasked us to build a tool to increase the amount of calls a call center agent can handle in a day. So to help them process those calls faster. Our solution was a web app the agent has on a second monitor. It's always open, and it shows static and real-time information about the ongoing call. Static, something like who's the customer, what subscription package is he on, but also real-time information like the transcript of the call intent, what was the call about, and question the agent should ask in order to advance the conversation more smoothly and maybe even faster. This oh, sorry. Where's my mouse? Exactly. So we were tasked to build a POC. And for this talk, I want to focus on the third feature here, the potential checklist. Because we built a wide array of features, but I think we can see all the problems we faced with just a single feature. And to give you a clear understanding of how this feature works, I brought a short demo here. So on the left side, on the green, you will see the UI the agent used, and on the right side, you will see the transcript of the call. Call starts off with our agent saying, "Hey, welcome to Meal Kit Delivery Company. My name is Sarah. How can I assist you today?" Customer says, "Hi Sarah, my name is Thomas. I'm calling because I have some issues with my latest meal kit delivery." "I'm sorry to hear that, Thomas. Could you please tell me what's wrong with your delivery?" And then the customer says, "Sure, I noticed that one of the ingredients was missing." At this point of time in the conversation, we are able to identify a call intent. Call intent is missing ingredient. If we have that call intent, we can look into a database of the company and we can find out there's a clear script the agent has to follow. There are a couple of questions he has to answer. So from a database, we can retrieve the list of questions the agent should ask the customer. For example, what's the address, which ingredient was missing? And then if we play out the conversation, the agent says, sure, can you tell me which ingredient was missing from your delivery? And the customer says, sure, I opened the package. It was supposed to include some fresh basil, but it wasn't there when I opened the box. At this point of time, our tool automatically ticks off the ask question so that the agent knows, if he looks on his monitor, which questions to ask, which he already asked. And this not only helps to keep track of the conversation and move that along faster, but also helps us to ensure that we gather all necessary information. So yeah, with that tool, let's look a bit of the proof of concept. We had 4 weeks to build this. We were 4.5 team members, 2 engineers, 2 data scientists, and we had a front-end engineer for 2 weeks. We had to do agent interviews, call shadowing. We gathered data like the list of questions. We had to design the cloud architecture, build the data pipelines and the front end. And at the end of the 4 weeks, we went live with 20 test agents to A/B test the tool if it actually brought any benefits. This fast development is great to see early results, but of course, during development, as you probably know it, a lot of corners were being cut to being able to deliver after 4 weeks. And we will see in a few minutes how that impacted our scalability. But first, let's take a quick look at the architecture. So we start off on the left side. We have our customer and our agents. They connect on a telephonic platform. This is where the agent picks up the call. This sends out the data stream to our first building block, the audio stream consumer. And this sends then the audio bytes to a transcribe engine. This output text. Text gets put into our process transcript pipeline. So transcript is just a transcript of the conversation. The process transcript pipeline does some LLM calls. An LLM call could, for example, be super simple prompt. Hey, review the support center transcript provided below. We insert the transcript here. Did the agent ask the customer which ingredient was missing from one package? Respond with yes or no. Answers to LLM questions and the transcript are then stored in a database. And we have a front end with calls and API. The API looks into the database and serves the data to our agent. This whole thing was built on AWS, pretty much everything serverless. And yeah, this architecture looks fine, but when you think about this application, it's a real-time application. We are very much interested in the latency. This tool would not be of much help if, for example, the agent asks the question and only like 40 seconds afterwards, the question was ticked off, because then he finished asking the question, he looks over to his monitor, he looks which questions they have left to ask, and he still sees the asked question. They're not being ticked off. So let's look at the data flow, and let's look at what kind of latencies different steps in this process introduce. So yeah, we start off and we are especially, maybe I should clarify this, interested in a data flow from start. Agent finished asking a question, so the last word left his mouth, and the end is the question is being checked off in the front end. Yeah, we start off with the telephonic platform. We have a 1 second delay there until the audio bytes reach our consumer. Our consumer receives those audio bytes and he buffers them for 10 seconds. He then takes the 10-second audio byte array and sends that to a transcribe. It's a pretty much basic API call to Whisper or AWS transcribe. This takes about 4 seconds to transcribe the 10-second audio file. This is including upload time of the 1 megabyte payload and all that stuff. We then send the text we receive from the transcript back. No, not back, but we send it forward to our process transcript pipeline. We have a couple of LLM calls there, 4 or 5 on average, take about 8 seconds. We used AWS Bedrock for that. And we have a couple of database calls. I think it was 8 reads and 2 write calls. Together take half a second. And lastly, we have the front end. There we implemented a polling mechanism. So every 5 seconds, the front end would just call an API. The API would look in a database. If the data was there, it would return it something. So depending on when the data hits the database, we have a delay of between 1 and 5 seconds. If we count that all up together, we have a delay of between 15 and 25 seconds until the question is checked in the front end. This is what we delivered after 4 weeks, and then we went live. We had 20 agents who tested the tool. We had 20 agents who didn't test the tool. We had some control groups, did some tests, and after a week, we came back to the customer, and they were really happy with it. They thought the solution was beneficial. They saw the potential, and they wanted us to continue to build. They had two hard requirements. Our primary objective, first of all, latency reduction. They wanted us to achieve and maintain a latency of under 7 seconds for the data pipeline I just shown on the last slide. And secondly, scalability. So they wanted to roll it out to the whole department of call center agents, which was about 200 of them. I can give you a short spoiler here. This to achieve those two things, took over double the amount of time to build the whole POC, including coming up with the features and all the stuff. So there's so much work and so much also unexpected work that went into this. There's so much tech debt we left, like it was us and nobody else's fault. There was scalability issues which we did not think about before. We learned a lot along the way, and I want you guys to take something home today as well from this talk. So I'm going to show you like a bunch of errors that we encountered, and maybe some of them you see in your own application, or you see like this pattern I use as well, and then you make a mental note. If I want to scale it, might have to think about this part again. So yeah, let's jump into the changes we made, and I think we should start off with reducing the latency first. We see red blocks are bad, green blocks are good. We have a lot of red blocks. At the moment, we are between 15 and 25 seconds. We need to get that down. We basically need to reduce the whole array of delays we get. So first one, telephonic platform. Unfortunately, customer was set on a specific telephonic platform. We couldn't get them to change that. 1 second delay, it stays. Second is the audio stream consumer and transcribe block. So actually our consumer was built pretty well. It consumes the byte really fast, but it of course adds a delay when it buffers them for 10 seconds. The reason we initially buffered for 10 seconds was because the transcribe quality improves the longer the audio file you have, until a certain length, of course. And second of all, we had trouble with words being cut off in the middle of the word. And the longer you buffer, the less risk you have of that happening, of course. How did we get around this? We basically changed our whole architecture. We shifted from a file-based transcription service to a real-time streaming transcription. We used AWS Transcribe Streaming for that. It has some limitations, but in the end, it really, really made a difference. So basically how it works is when the call gets picked up, we open a transcribe stream, and then the audio bytes that come from the telephonic platform, we convert them and we send them directly into the transcribe stream. Asynchronously, the stream then has an output stream which returns words, single words. It takes about, like we always send in 1 second of audio, and it takes about half a second for this 1 second part to be transcribed. And the streaming transcribe block uses the context of the last couple of seconds to identify the words. We get the words back and we buffer them as well. We buffer until we hit a full sentence. So now you might ask, you're still buffering and a sentence can even take longer than 10 seconds. So did you actually gain something? Yes, we did. If we go back to the pipeline, you see that we start off with the agent finishing the question. So we are already at the end of the sentence. So we don't have any delay there anymore. We only have half a second delay until the last second of the question is transcribed. If this is such an improvement, why didn't we build it in the first place? Simple answer, was super, super complicated to implement. It took us over 3 weeks to refactor the code. We had to move our consume and our transcribe block from our pretty much stateless service into a Lambda, into an AWS Lambda, because they had to be isolated from the other calls that were happening at real time simultaneously. And I don't know if you work with Lambdas, but multi-threading in Lambdas is not an easy task. And yeah, those 3 weeks, we basically didn't have time to do that in the POC. So if I would have to do it again, I would still use the file-based transcription in the POC, because I think that's the manageable thing to implement. So yeah, Lambdas work great for us, but of course they have a little bit of a cold start. But yeah, we improved this part. Let's look at the process transcript pipeline. There, pipeline takes about 8.5 seconds. Most of that is LLM calls. We have a bunch of LLM calls. And I know I said this already, but when you develop fast, a lot of errors creep into your code. A lot of things are not really optimized and inefficient. And we looked through every LLM call, and those are a couple of things we found. First of all, we could, of course, identify some super long, unnecessary LLM calls. We could parallelize LLM calls which were not dependent on the outcome of the previous LLM calls. And what we did, which had a great impact, was we classified our LLM calls in 2 categories. Simple, like something like answer with yes or no, and complex one, like a summarization task or something. And we assigned different models for this different classifications. So we used a way smaller, tiny model for the simple questions. So the same performance, but the model is way faster. And so we gained some seconds there. And we even found 1 or 2 LLM calls which we could get rid of entirely by just using a standard NLP Python package, something like Spacey. It actually can solve a lot of problems, but you kind of forget when you're in the Gen AI flow and just think, yeah, I'll just ask the Bedrock to answer me this. But we, of course, were left with some long queries, and there we looked at the prompt length, at the input token size. Input token size closely related to response time, and we tried to reduce those. So we easily gained 5% less input token by just, instead of saying agent double point and customer double point, just saying A double point and C double point. We found other ways to shorten our transcript. For example, we had an LLM prompt, if I remember correctly, I think it was, did the customer say his name? And if so, what was his name? For this LLM prompt, we sent the transcript as context, but of course you don't need the full transcript. You can only send the parts of the transcript the customer said. You don't need to send the agent parts. We could reduce our prompt there. Or, for example, we had an LLM prompt that said, was the customer satisfied with the call today? For this one, you also don't need to send the full transcript. It's enough to send the last half of the transcript, because the customer would never talk about if he was satisfied with the call in the first half of the transcript. So yeah, we did a lot of stuff there and managed to reduce our time from 8 to 4 seconds. Next up, database calls. So it doesn't look like much, 0.5 seconds, and maybe doesn't make a big impact in this particular flow to optimize them. But since we're scaling up to 200 users after improving the latency, and we have some pretty big tables, for example, that our transcript table or our customer table with 500,000 entries, it is always good to look at your SQL queries and see if you can optimize them in any way. For this project, we used an AWS, RDS, Aurora Postgres database. And this database has actually a super nice dashboard. You can go on there and you can see what queries hit your database in the last 24 hours, and you can sort them by how long they took. We did that. We took the top 20 queries and we said, let's analyze them. What did we find out? We found out that the first couple of queries weren't even from a real-time pipeline. We had a daily customer behavior analysis notebook running on SageMaker And we looked into the notebook. First line of the notebook, select star from table. Second line, filter on in pandas, like filter on only yesterday. And the third line was like, take only those 3 relevant columns. So what did we do? We, of course, adapted that and said, yeah, you always have to select the specific columns and have all your conditions in the SQL query. This stuff that happens, and it's okay that it happens if you develop fast, but you need to know where to look in order to find it, and find it again and resolve your tech debt, basically. So for our queries, which were really used in our tool, we did an explain analyze on most of them, looked if the execution plan looked correct. We added some indexes. For example, we didn't have an index on the email column. We did have an index on the phone number column because we knew agents looked up customers by typing in their phone number. But what we didn't think about, agents would mostly only look at the most right 9 digits of the phone number, and we didn't have an index on that part, so we created new columns. We did a lot of other stuff, which in this picture here doesn't add up to a lot, but it helped us later when scaling a lot. Front end, as I said, we use polling. We use that because it's super, super simple and fast to implement. We ended up switching to WebSockets. I was a bit afraid of that, but actually with Fast API, it's super, super easy to implement. And it worked out great. I would say half a second of delay, that's estimated. In the end, if we add that all up together, we managed, we got it, we did it. We ended up getting to under 7 seconds to 6.3 seconds. Now, does it work with 200 users? Let's look at the scale up. Scaling from 20 to 200 users, that's a 900% increase. We know that about 75 of all agents are in calls at all times, 24/7. And that means that we have 150 agents using the tool around the clock. 150 agents, that's 150 Kinesis data streams. That's 150 simultaneous transcribe streams. We know that we trigger the process transcript pipeline with every sentence. There are about 6 sentences per minute, so we have 900 pipeline invocations. Pipeline has about 10 database calls, 9,000 database transactions, and about 4 to 5 LLM calls, so we have over 3,000 LLM requests a minute we had to handle. I know that's a lot of numbers, but I quickly want to take a moment to emphasize on 3,000 LLM requests a minute, on what amount that is. If we, for example, were not to build a real-time call center tool, but a chatbot, with 3,000 LLM requests a minute, we could handle over 100,000 users easily, saying that every user visits the chatbot twice a day and types in 5 questions or something. So it's a lot. And it turned out in the end to cause us a lot of troubles. Anyways, we're happy with the pipeline. We went live with 200 users for just a day, just to test it. Expectedly, everything failed, everything crashed, error alerts through the roof, everything froze, the agents didn't see anything. But we identified a couple of points of failures. First of all, AWS quota limitations. I think this was an obvious one. You're only allowed to have 25 transcribed streams at all times simultaneously. You're only allowed to have 75 Kinesis streams. This is a simple issue, but a tedious one. We had to contact AWS support. This was a really big blocker for us for a long time. We couldn't continue development and testing, but in the end, it got resolved. And once it got resolved, we saw that our process pipeline had increasing processing time. It took forever. We had timeouts and occasional failures. We looked deeper and saw that our database was bottlenecked, so requests were timing out, CPU load was over the roof, and also our LLM service, surprisingly, our response times didn't stay in under 4 seconds, they went up to over 10 seconds. So yeah, let's look at the architecture on where this happened. Red, again, bad. We have the first problem with the transcript pipeline. And this is the same which happened in the API because they were both in the same container. There, We were using an Elastic Container Service, ECS, had a Docker image with our Fast API server hosted. And in theory, the ECS should just scale. We set it that every time the CPU load hits like 60%, the instance size increases. And we thought we would be fine with that. But as it turns out, we had used multiple workers for Fast API, like we used GUnicorn to use 4 workers for Fast API, and the ECS couldn't pick up on high CPU load if 3 of the workers were tolling out at 100% CPU, but one of them was fine. And it turns out if you use 2 measures of scalability, they can sometimes clash with each other. So we switched back and started a Fast API with the standard UVcorn, only 1 worker, and it worked. The ECS picked up on the CPU load, was able to increase in size, and we saw way better performance on that front. Next up, LLM calls. We had many discussions and many calls with the AWS Bedrock team in London, and they promised us, yeah, 3,000 LLM requests a minute, easy, we can handle that. They couldn't. We weren't being cut off. We didn't hit any limitations and didn't get any error responses. But when we looked into the Bedrock dashboard, we were just soft throttled. They would like queue our calls. We had an invoke latency which went like up to 20 seconds. So we had to escalate that like super, super high, super many like calls and senior people involved. At the end, they had to get like physical people into the data warehouse, install more compute for us. I think they didn't like us very much, but in the end, we were able to get our throughput. It took us even like longer than the project was supposed to, but we managed to get that. Database, we saw high CPU loads. We saw that requests took longer than we expected. What did we do? We just put more money at it. We said like, yeah, let's have 8 cores instead of 2, then that way we can handle 8 transactions at the same time. Didn't help much. It helped, but not as much. Then we said, okay, we went from 1 read, 1 write instance to 3 read, 1 write instance, and we even made sure that all like select statements use the endpoint only for reading and all the insert statement only for writing helped as well, but still, database CPU was way higher than it should be. We took a closer look in the RDS dashboard and we found out that the database did not only need to handle 9,000 requests a minute, it also had to handle 9,000 authentication attempts a minute. This was because our API stateless. Every time an API request comes in, opens the database connection, does the call, and closes it again. As it turns out, databases are very fast in handling transactions, but not as fast in handling authentication. We fixed this by just adding a database proxy, which has one stable open connection to our database, so that the database doesn't have to handle authentication anymore, and we would authenticate against the database proxy. Yeah, with that, actually after a lot of work, we tried it again. We went live with 200 agents, and it worked out in the end. This was last year. I think the pipeline still runs to this day. Yeah, to conclude, the real work begins after the POC. As illustrated in my work, we needed 2 months to refine the project without adding any new features, without improving the output quality. And managers and clients often asked for that. But like this was such a time-intensive effort, and I feel like it's often underappreciated, especially when stakeholders focus on immediately visual outcomes. It's essential for project managers and clients to understand that this journey from POC to market-ready product involves many engineering efforts and lots of time. So let's recognize that the importance of this stage, not just for the technical challenges, but also for the long-term success of our products. And thank you very much. I am happy to address any questions you have.